So in this video, we're going to look at receptors, both Pacinian corpuscles and the photoreceptors of the eye. We're going to start with Pacinian corpuscles. Here is a Pacinian corpuscle, which is basically a pressure receptor associated in our skin. So we have labeled here a sensory neuron. Over here we have our myelin, made up of Schwann cells. And here we have our node of Ranvier. Our node is the only place at which depolarization can take place. And then right at the end, which is where we're interested in, we have these lamellae, which are folded around the end of our sensory neuron, the tip. And these have within them sodium ion channels, which are stretch mediated. Now, what do I mean by a stretch mediated? Well, if you press on this Pacinian corpuscle, I'll do it down here. If you only press lightly, you're going to slightly distort that Pacinian corpuscle. If you press heavily or slightly heavily, then you're going to distort it even more. If I press it even more, I'm going to distort the lamellae even more. That opens up the stretch mediated sodium channels. So pressure opens the stretch mediated Na+ channels. And if the threshold is reached, and that is important, we'll come to that on the next slide, a generator potential is created. So I'm going to look at the next slide. We're going to look at an example of this. So we have here a neuron in which we have microelectrode A and then microelectrode B over there. Okay, those are measuring the potential difference of the membrane potential. So in the microelectrode A, we're looking for a generator potential. Microelectrode B, we're looking at the actual action potential within the sensory neuron. So if we look at microelectrode A with light pressure, what you will see is, yes, we get some depolarization, but it doesn't reach my -50, which is my threshold potential in this case. So because it never reaches that, we don't generate an action potential within our electrode B. However, if we put slightly more pressure on, medium pressure, then it goes above -50 for approximately 1 point something milliseconds, 1.2, 1.4, which generates a low frequency of action potentials in our microelectrode B, in our sensory neuron. If, on the other hand, we put heavier pressure on, it now goes above -50 for a longer period of time, because it goes up to -40 and then back. And that is seen to generate, and I'll draw them in, a higher frequency. Right, it should be right to the same height, slightly misdrawn there. We'll just add that in. Okay, a higher frequency of action potentials. It doesn't change the depolarization. It will still reach +40 because that is the all or nothing law. But we have more per second, and that gives us an indication of how much pressure we are providing. Okay, we're going to move on now to photoreceptors of the eye. Photoreceptors of the eye are found in the retina. So if we have a think about roughly what the eye looks like, you don't need to know the structure of the eye, so I'm not going to go on about it. We have the optic nerve at the back here. We have the scleral layer, which is the whites of your eye when it appears at the front. Not really interested in that layer either particularly. We then have the choroid layer, which we will come to later. So I'm just going to draw that in black. And then finally, sitting on top of that, which I'll draw in red, we have our retina, which includes like that. And our retina includes our fovea or our yellow spot, which we will see is really important. So photoreceptors are found in the retina. Remember, light is coming in this direction, like so. And there are two types that we're going to look at, which are rods and cones. Rods are sensitive to low light intensities, but only allow us to see in black and white. Cones are sensitive to higher light intensities and allow us to see in color. And there are three types of cones, red, blue, and yellow, that detect different wavelengths of light. And it's the combination of them, it's called the trichromatic theory, that allows us to see different colors. Okay, so if you stimulate your blue and your yellow, you will see a different color than if you stimulate your red and your yellow at the same time. So if we look at the retinal structure, so if you imagine taking, okay, so this is what we've done, is we've taken the eye and we've taken the retina and we've opened it up like this to give us a flat surface. Okay, so this is one side of the eye going all the way around back to where we started again. And what you will notice straight away is if we have a look at the cones, there's very few cones anywhere except at one point, which is here. And that point X is the fovea. That spot at the back. If I go back, you'll see that is that fovea, the yellow spot, or fovea. Okay, so it's called a yellow spot because that's how it looks when you look through the eye. Fovea is the proper name for it. So here is our fovea where all our cones are found. And that is because when you're looking at something in bright light, which is when you use your cones, your pupil is really, really small. So therefore, the light that hits is all going to hit. So if you imagine a really small pupil, there's my iris, all the light's pretty much going to hit on that fovea over there. There are no cones or rods at this particular point here. That is the blind spot. You find no photoreceptors there. Luckily, it doesn't matter. We've got two eyes, so we can, what we don't see with one eye, we see with the other. If you have a look at the rods, you will see that, yes, there are none in the fovea. As you go away from the fovea, you get more. So they are situated more if we go here and here, like so. And that is because when your pupil is open wide, because you are using low light intensity. So if I open up my pupil, like so, then light is more likely to hit there and there. And so you have your rods there. Obviously, towards the periphery of the eye, like there and there, you're not going to have many rods at all because nothing really is ever going, low light is actually likely to reach that part of the eye. You do need to know this graph. You need to recognize the fovea, recognize the blind spot, and recognize the pattern of photoreceptors. Okay, so if we look in more detail at the retinal structure, okay, so let's give you an idea of where we are here. Okay, this over here is my choroid layer. My light is coming in this direction from through the cornea and through the pupil, and it has to travel through all of these until it gets to the rods and the cones over here. Now, these are the ones I'm interested in. These are called bipolar neurons. Okay, the ones over here are called ganglion, but I'm not too interested in them. And then I'm interested in the actual photoreceptors over here. So we've got over here, these are 6 and 7, which are my rods. I know they're my rods because, first of all, the shape of them, they tend to be, sorry, my apologies. So next I'm interested in the photoreceptors. If we have a look over here, number 6 and 7, these are my cones. I know they're my cones for two reasons. A, they're fatter, so they're more cone shaped. But B, they each have their own bipolar neuron, which is going to become really important. Whereas number 1 and 2, they are my rods, as is number 3. And you will notice they share bipolar neurons. So 1 and 2 share one, 3 and 4 share one. And you've got a sharing over here going on between 3 of them, that one and that one all share a bipolar, and that's going to become really, really important. Okay, so if we have a look at how rods work, so let's think about the dark. So when we label a rod, first of all, if I go back, okay, we're looking at labeling one of these like that. Okay, so light is coming. We've got the in this direction. Okay, it's going to come all the way through, and eventually it will be absorbed by the rhodopsin pigment, which is in our outer segment. So we have our outer segment, our inner segment. There's lots of mitochondria here because this is going to be a very active process. So what actually happens in the dark is that the sodium channels in the outer segment are open, and sodium ions are actively transported out of the inner segment and diffuse back in through open sodium ion channels in the outer segment. So this is a form of facilitated diffusion because they're moving through a channel. And this means that actually we've got depolarization going on here because we're constantly removing positives, but they're going back in again. So we've got a slightly positive, ever so slightly positive rod. And this causes a release of neurotransmitter, and that neurotransmitter is inhibitory. And therefore, because it's being released and it's inhibitory, there is no action potential in the bipolar neuron at all. But let's think what happens in the light. So here we now have some light coming in. So light is going to be absorbed by the rhodopsin. And when the light is absorbed by the rhodopsin, it gets broken down into something called retinol and opsin, and that closes the sodium ion channels that are within the outer segment. So I'm going to move that out of the way. So we now have no ability for the sodium ions to come back in. That is now not possible. But our sodium ions are still actively removed. So we still got the active transport of sodium ions out, but they're unable to come back in. And the effect of that is to make the rod hyperpolarize, very, 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 very negative. And the effect of that is to stop the neurotransmitter being released. And therefore, we get an action potential in our bipolar neuron. Now, they're unlikely to ask you a question solely about this without any prior information, but I have seen it come up in an exam where they show you what happens in the dark, and they ask you to sort of explain some of the terms and some of the processes. So it's worth understanding what's actually happening. The most common bits, however, for them to ask you about is the next bit, which is the sensitivity versus visual acuity. So we're looking back at the rods here, and what we notice is we have 3 rods. Number 1, number 2, number 3, all feeding into one bipolar. Now that has its advantages because it means that if a small amount of light falls on each rod, the retinal convergence, which is what we call this, or the summation, is going to be enough that you're going to reach the threshold and generate your action potential, because the neurotransmitter is going to mean that we have enough of a threshold potential to reach our action potential. However, there is a negative aspect to it, and that is the idea that, let's imagine I had 3 letters rather, M, something, A, beginning of a word. The problem is that's going to send an impulse, that's going to send an impulse, but it's all going to the same neurons. So all you're going to see is a mush of the M and A. It's not going to be able to distinguish between it. It's why you can't read small print in the dark, because you don't have a good visual acuity with your rods. You cannot distinguish 2 points close together. A really common question is to explain why rods have a low sensitivity to light. In other words, they can sense low light intensities, but why that has a knock-on effect on visual acuity. So rods can detect low light intensities because of the retinal convergence, which means a small light intensity on each rod causes an action potential in the bipolar. But because 3 rods connect to one bipolar, they cannot distinguish between small dots close together, which means they have a poor visual acuity. On the other hand, if we look at cones, they have their own bipolar. Now that's good, because by having your own bipolar, it means that you will be able to see 2 things that are close together. You will be able to distinguish and see the space, but the negative to that, the counter argument, so to speak, is that because of that, because they each have their own one, if low light intensities fall on my bipolars, it's not going to be enough to generate an action potential. So cones are only sensitive to high intensities of light. So the advantage of having one bipolar to one cone is you have good visual acuity. The negative is that you have poor sensitivity. The advantage to rods of having 3 rods to one bipolar is that you have greater sensitivity. You can sense low light intensities. The disadvantage is you have low visual acuity. So you can't have both at once. You need to be aware of which one you are talking about.